In this video, we will explore the fascinating concept of countable and uncountable infinity. These ideas help us analyze the limits of computation and the nature of problems that can be solved. Before diving into these concepts, let's briefly discuss the mathematician George Cantor, who proposed that there are different sizes of infinity. Cantor's work was met with ridicule and opposition from many of his contemporaries. The idea that some infinities are larger than others seems paradoxical and unsettling to many mathematicians of his time. The rejection and criticism of his work took a toll on his mental health. He suffered from severe depression and was hospitalized multiple times. After his death, his work laid the foundation of modern set theory and drastically changed how we understand infinity. Before understanding infinities, we must review one-to-one correspondence. Two sets have one-to-one correspondence if there is a bijection between them. A bijection means the mapping is both one-to-one, injective, and onto, surjective. One-to-one implies that each element in set A maps to exactly one unique element in set B, ensuring no two distinct elements in A maps to the same element in B. In the first example, each element of set A maps to unique element of set B, whereas one element of B is not mapped to any element of A. This is still a one-to-one relationship. In the second example, two elements of set A maps to the same element of set B, which is not a one-to-one relationship. Onto implies that every element in set B is paired with at least one element in set A, ensuring no element in set B is left unmatched. In the first example, both elements of set B are matched with an element of set A, making it an onto relationship. Whereas in the second example, a few elements of set B are not matched with any element of set A, which is not a valid onto relationship. When two sets have both one-to-one and onto relationship, they are said to have one-to-one correspondence. Note that if two sets have finite number of elements, they can have one-to-one correspondence if and only if they have the same number of elements. This concept was extended by Cantor to infinite sets. Now let's start with the definition of countable infinity. A set is countably infinite if it has one-to-one correspondence with natural numbers. Recall, natural numbers are 1, 2, 3, 4 and so on. Another way of looking at this definition is that given infinite time, you would be able to list all the elements of countably infinite set. That is, one should not be able to think of any element X of the set that will not eventually be listed, given infinite time. A simple example is the set of natural numbers itself, which is clearly countably infinite since each number maps directly to itself. What about the set of all integers? At first, it may seem that we cannot establish a one-to-one correspondence with natural numbers, because if we start mapping positive numbers first, the negative numbers will be left out, and vice versa. However, if we alternate between negative and positive numbers, we will be able to list them all. That is, we start with 0 and map it to 1. Then we move it to -1 and map it to 2. Then to 1 and map it to 3. Then to -2 and map it to 4. Then to 2 and map it to 5, and so on. This alternating method ensures that every integer is eventually assigned a unique natural number, proving that the set of integers is countably infinite. An even more interesting case is the set of all positive rational numbers, which are the numbers that can be expressed as fractions of integers, such as 1 over 2, 3 over 4, 7 over 1. The set of positive rational numbers is countable. To see how this works, imagine arranging the rational numbers in two-dimensional grid, where the numerator is on the y-axis and the denominator is on the x-axis. Thus, the first row of the grid will have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. The second row will have 2 over 1, 2 over 2, 2 over 3, 2 over 4, and so on. Similarly, we can write other rows. Notice that each row as well as each column contains infinite many elements. A naive approach such as going row by row or column by column would fail, because we would never be able to escape that row or column, leaving infinitely many fractions uncounted. Instead, we alternate between both rows and columns in a structured way. We begin with 1 over 1, then move to 2 over 1, then 1 over 2, then 3 over 1, then skipping 2 over 2, then 1 over 3, and so on. As we follow this diagonal pattern, we skip any fraction that are duplicates of simpler ones, such as 2 over 2, which is same as 1 over 1. A straightforward way to determine which fraction to keep is by computing the greatest common divisor, GCD, of the numerator and denominator. We only include a fraction if its GCD is 1, meaning it is in its simplest form. For example, we exclude 2 over 2 because its GCD is 2, but we will include 1 over 1. By following this structured process, we ensure that every rational number appear in our list at some point, proving that the set of all positive rational numbers is countably infinite. You might be wondering how to implement this graphical proof using loops. Here is a C code that I have written, which will list all the positive rational numbers if given infinite time. That is, no fraction, say x, from the set of all rational numbers will escape this loop. Feel free to copy and try this code yourself. Now, what exactly is uncountable infinity? A set is called uncountable infinity if it is infinite and does not have a one-to-one correspondence with the natural numbers. In other words, there exists an element x that will never be listed, no matter how cleverly we try to enumerate the set. The most famous example of uncountably infinite set is the set of all real numbers, which includes both rational and irrational numbers. In fact, even the real numbers between 0 and 1 form an uncountably infinite set. Let's prove this by contradiction. Assume for contradiction that the set of real numbers between 0 and 1 is countably infinite. This means there exists a function f of n that maps each natural number n to a unique real number in this interval. For example, for natural number 1, the function might return the real number 0.14159 ... For 2, it might return 0.555 ... For 3, it might return 0.12345 ... For 4, it might return 0.511100 ... and so on. Cantor's famous diagonalization method demonstrates that we can construct a real number x that is not in the list. To do this, we define x such that its ith decimal place differs from the ith decimal place of the ith number in the list. For instance, in our example, the first digit of x differs from the first digit of the first number, so it cannot be 1. The second digit of x differs from the second digit of the second number, so it cannot be 5. The third digit of x differs from the third digit of the third number, 0.12345, so it cannot be 3, and so on. Following this process, we construct a number x such as 0.2112 ... By design, x differs from every number in the list at least one decimal place, meaning it cannot appear anywhere in the enumeration. This contradicts our initial assumption that the set of real numbers between 0 and 1 is countably infinite. Therefore, the set of real numbers in this interval must be uncountably infinite. This concludes this video. If you found it helpful, please consider supporting this channel so that I can create many more such videos. See you in the next video. Bye.